Hello everyone, I'm Deepak, and today I'll present this topic preview on the very exciting topic of 5G networks. We've all heard about 5G, and there's just been so much excitement around this topic. And that's because 5G provides many new functionalities and is critical for many applications. For example, 5G will include high bandwidth, gigabits per second speeds for wireless network connectivity for applications like virtual reality, extended reality, and the metaverse in general. It will also have primitives for low power, low cost connectivity for billions of IoT devices that are being deployed across the world today. And finally, it will include ultra reliable, low latency connectivity primitives that are essential for applications like digital healthcare or autonomous driving, where both ultra reliability as well as low latency are essential due to the critical due to the critical nature of these applications. In this talk, I'll provide some basic terminology and background for people who are new to the area so that they can appreciate the talks in this session. And then I'll talk about some key challenges in the 5G networking research space. And I'll conclude with a quick overview of the papers that we are discussing today. So to get started with the terminology, the first part of the network is the RAN, or the radio access network. This is how your smartphone talks to the base station or the cell tower next to you. Okay. So this is called the radio access network. And in 5G, the new part of this radio is called 5G NR, or the new radio, which is a unified radio interface for 5G. It includes many new specifications, modulations, which I'll not go into the details of. At a high level, the base station is called G Node B, where G is for next generation, strangely. And the client is UE. So at the RAN level, 5G uses multiple frequency bands, and I'll go in the details of these bands in a bit. And one cool primitive in this space is massive MIMO. Essentially, in massive MIMO, the base station uses tens to 100 antennas to either communicate with multiple client devices simultaneously or to provide other kinds of functionality. Okay, so we talked about the RAN. The other part of this network is called the core, which enables many core network functionalities. So once your data goes from, so RAN deals with your data going from your smartphone to the base station or your cell phone to the base station. And the other functionalities are all being dealt with the core. So for example, authentication of the user, that, hey, is this person authorized to use my network? Or mobility, that is, if you move from one base station to the other, as you walk through the city, as you drive through the city, that is all being handled by the core. So one new part in 5G is that increasingly, the implementation of the core is moving from hardware implementations in previous generations to software-based implementations and moving to cloud deployments. So these different network functions also provide APIs for them to interact with each other. So as I said, in the networking layer, the physical layer, there are multiple frequency bands in 5G. So at a high level, we can divide them into three. So there's the low bands, which are below 1 gigahertz, which are the traditional cellular bands. They provide long-range connectivity, but they do not have as much available spectrum. And as a result, they cannot provide as high bandwidths. Then there is the mid bands, which go from 1 gigahertz to 6 gigahertz. And basically, this is, I believe, one of the most popular band for deployment of 5G today. So existing deployments largely function in this band. So one example of the mid band is a C band from 3.7 to 4.2 gigahertz in the US. You will also see papers that do measurements in networks in China, and they perform measurements in the 2.6 gigahertz band, which is also a mid band. Okay, and finally, there's the high band, or the millimeter wave band, which exists 24 gigahertz and above. And these bands have a lot of high bandwidth and a lot of available spectrum, but at the same time, they suffer from more attenuation. So as you go from the low bands to the high bands, you have higher bandwidths, but at the same time, you have more attenuation in the network, which means your range gets reduced for the same power. And then you also need to manage this network a little better. Okay, so the final piece of terminology that I want to talk about is the standalone versus non-standalone deployments. So the idea is that as we move from 4G to 5G, we don't want to discard all of the investments that we've already made in 4G, right? So we want some kind of phased, gradual deployment of 5G. In NSA, or the non-standalone version, it largely relies on existing 4G core infrastructure. It uses the new radio, like the 5G new radio implementation, but it might be multiplexed with LTE and largely uses the same core infrastructure. In standalone deployments, there are independent 5G core and radio deployments that exist independent of 4G. Of course, like something like that has higher cost, but it can also enable full 5G functionality because both the core and the radio are now 5G. Okay, so that's all I wanted to talk about in terms of terminology and background for understanding 5G. And I think with these terminology, you should be able to appreciate the research that will be presented in this session. So let's talk about some of the high-level challenges that exist in this 5G space. So the first challenge is mobility and handover. So imagine that you're driving through a city or from one city to another. Clearly, your phone cannot be connected to the same base station throughout, so it has to move from one base station to the next. How do you handle these handovers? What are the implications of these handovers on applications? So all of that is something that we'll talk about in this session. Okay, so there are two kinds of handovers. So one is this horizontal handover, when you move from one base station to the next. And then there's also vertical handover or a technology handover, so as to say. And what that means is that you're moving from 5G to 4G or 4G to 5G, depending on what works better for you within the same base station. So for example, if I'm connected on a 5G millimeter wave network to the base station, but my network is blocked by someone, it might be better for me to move to 4G, right? So that's a vertical handover. And again, like there are questions as to how to deal with that efficiently and with minimal impact and disruption to the end user applications. Okay, so the second part of the 5G network is the core design. Again, don't like pay too much attention to the thing on the left. It just like shows how complex the core is. You don't have to understand all of the acronyms. But as I said, in 5G, the core is moving from hardware to the software. It needs to maintain its high performance and scale to like many devices, high bandwidth, while maintaining low latency. And it has to support multiple functionalities. So clearly, this is a challenging piece of software design, and there are this scope for many software optimizations. And finally, in a network as complex as this, you can imagine diagnosing and handling failures is hard because failures can occur at different points in this network, in the RAN, in the core, in the data plane, the user plane. So all of these failures are possible. Diagnosing where failures are happening and taking and handling them is a big challenge. So we'll have some like discussion and solutions for these challenges in the papers that we discussed today. And I'll give you a quick overview of these papers to conclude my talk. So the first three papers in this session are more measurement heavy. So they perform measurements from different contexts and different perspectives to give us insights into these networks and present new ways to solve these challenges. The first paper is called Vivisecting Mobility Management in 5G Cellular Networks. It deals with the mobility and handover problem that we talked about. And commendably, to understand mobility issues in networks today, the authors drove through 6,200 kilometers to collect measurement data in real 5G networks. And the key questions they ask are, what are the consequences of mobility management or handover practices that are being deployed today? So for example, if I'm doing a video call and driving through 3 cities, then will my video call sustain? What kind of issues will I experience? And then the next question they ask is, how can we improve mobility management for future deployments of these networks? And as you listen to these talks, remember that handovers can be both horizontal and vertical, and this paper deals with both of them. The second paper in this session is called Understanding 5G Performance for Real-World Services from a Content Provider's Perspective. So this paper studies 5G networks from a content provider's perspective. So imagine that you are deploying a new video streaming app. Do your users who are using 5G experience better quality of service? And And if so, why? And if not, what are new strategies that content providers have to use to exploit the new capabilities provided by 5G? And again, this paper has very extensive measurements. It studies 5G networks used by 23 million users over 1 year in a crowdsourced live streaming app. The third paper is called Mobile Access Bandwidth in Practice, Measurement Analysis and Implications. So this paper studies uh, the bandwidth that users experience in practical deployments. So remember, like in the beginning of this talk, I said that, hey, 5G is going to get you 1 gigabits per second. So this paper asks, like, do users actually get 1 gigabits per second in practice? And if not, what are the reasons for this underperformance? Okay, and to answer these questions, it obtains network measurements from 3.5 million users in China using a bandwidth testing app similar to speed test. And the key, like one of the cool things about their paper is that they also get physical layer logs like signal strength and RSSI measurements from these devices in addition to bandwidth data. Okay, so as you see these like three measurement papers, listen to their talks, you see there are common themes that emerge from these three different measurement studies in different contexts, as well as from different perspectives. The fourth paper focuses on diagnosing and handling failures in 5G networks. This paper is called SEED, a SIM-based solution to 5G failures. And the question that this paper is interested in is how does one diagnose and recover from failures in a 5G network? And the key theme in this paper is to use collaboration between device and the infrastructure to diagnose and recover from failures at all layers, at the control plane, at the data plane, and at the data delivery layer. And finally, the last paper in this session is L-Square 5 GC, or a low latency 5G core network based on high performance NFV platforms. So as I said, in 5G, the core network functionality is moving from purpose-built hardware to software-based cloud-native services. And the key question for this paper is what kind of software optimizations can we perform to build a highly performant, scalable, low latency core? And this paper has multiple optimizations, both to the control plane and the user plane functionality to deliver significant latency gains for 5G core. So as you see, this session on 5G networks covers a large breadth and depth in 5G, and I'll highly encourage you to attend these talks. This session runs from 3:30 p.m. to 5 p.m. on the second day of the on the first day of the conference, which is Tuesday. I'll see you there. Bye-bye.